So for the benefit of the people who have just joined us on the video, a very warm welcome to you. This session will take about an hour, did this morning, and it's going to be on basic diagnostics using an FFT analyzer. It's not restricted to SKF and FFT analyzers. This session is what we would call portable, as in the knowledge that you're going to gain could be used with any FFT analyzer. It's possibly prudent to do a little bit of a revision, a recap of where we should be. So here we've got a little experiment to explain where the vibration signature is going to come from. We're going to be looking at vibration signatures in a short while. Where does that vibration signature come from? It comes from forces. The world of rotating machinery is dominated by Newton's laws of motion. So here we've got the second law of motion, force equals mass times acceleration. We have a machine sitting on top of some bathroom scales. In real life, you would possibly put force transducers under the feet of your machine. But in this case, we're using some bathroom scales to represent force going into the foundation. And one thing that we've learned in previous sessions is that no rotor is perfectly balanced. You can spend hours and hours balancing, but you'll never get to a point where there is no residual unbalance. Therefore, when we apply electrical energy, electrical power that goes into that machine, that electrical energy gets converted from electromagnetic forces into rotational mechanical motion. And we have an unbalanced mass that's rotating. That mass is exerting centrifugal force in all directions as it rotates. But in this case, our measurement device is only measuring in one plane. So the bathroom scales only measure in the vertical plane, and therefore if we plot the forces versus time, we plot this thing called a sine wave. For our purposes, for our diagnostics, we're going to be using an accelerometer. So we're going to be measuring the A part of force equals mass times acceleration. We use an accelerometer because it's much quicker and easier to apply to a machine. You just simply click it on. And it too measures only in the vertical plane, or sorry, in one plane, whatever plane that you put it. And so we can expect to see sinusoidal signals coming off that. And when we make our diagnosis using our FFT analyzer, one of the objectives is to get those forces down. So for example, if we measure excesses on balance, we want to get those unbalanced forces down. Therefore, we would go through the regime of balancing the machine, and there'll be a webinar next week on all of that, so we'll press ahead. Expanding to a more complicated machine, here we've got an electric motor driving into a gearbox. The same applies, but now we start to get multiple sine waves, and that's the reason why we need an FFT analyzer, to disseminate these multiple sine waves. So where do those multiple sine waves come from? Well, if we place an accelerometer onto our motor gearbox, we can expect those sinusoidal forces to radiate through the structure from the electric motor, through the casing, into our accelerometer, and we expect to see a sinusoidal signal coming from the forces generated by the electric motor manifesting itself as vibration. In this case, we have a gear attached to that motor shaft. If, for example, there are 22 teeth on that gear, for one revolution of the motor shaft, we're going to get 22 transference of force onto the gear teeth. So we might expect to see a 22 times. Now, I've used the word times there, and this is where this issue of harmonics comes from. You get multiples of the running speed, and you'll hear people saying there's a big 4 times, there's a big 22 times, there's a big 3 times. It's all multiples of the running speed. There's no real mystery at this stage. Each component that rotates will generate forces at the frequency at which they rotate, and in this case we get a 22 times. Thing to note is that there could be quite high forces in those teeth meshing. Those forces have to radiate through the structure or the steel of the gear into the shaft, into the inner race of the bearing, through the oil, through the ball or roller, into the oil again, into the outer race, into the casing, through the paint and out to the outside world. So in gearboxes, for example, it's very common to see very small signals representing quite high forces, so we have to be a little bit careful there. This is a speed reduction gearbox. This output shaft will not be perfectly balanced. So it too is going to start generating unbalanced forces at the speed at which it rotates, and we'll see sinusoidal forces subsynchronous with the motor speed. And there's a word that when I had a full head of hair and I started hearing people talking about subsynchronous vibration, what does that mean? It just means that we've got sound or vibration at less than the running speed of our prime mover, our electric motor. And rolling arm and bearings are a really good source of subsynchronous frequencies. All these signals radiate through our structure and become a complex waveform. Within the limitations of PowerPoint, that's as close as it could get to a complex waveform, but it just means that the signal, all those sine waves are added together and become a squiggly line. There's a Northern English term for a complex waveform. It becomes a squiggly line. So what do we need? We need any FFT analyzer. They come in variety of shapes and font sizes and colours. We need an FFT analyzer, and that FFT analyzer is going to do the math on our complex signal and break it back down into our constituent parts. So we do the Fourier transform. There's a webinar purely on the fast Fourier transform that you can download. So we now start to look at the vibration spectrum, where we've got vibration magnitude on the y-axis in whatever parameter you're going to measure, acceleration, velocity or displacement, and we have vibration frequency on the x-axis in whatever parameters you're going to measure, either hertz or CPM, cycles per minute. I'm a hertz man. Sorry about that. It's an affliction I've had all my life. So the process goes on. For each and every sine wave in our spectrum, if we're looking at a 1 kilohertz spectrum, the fast Fourier transform is going to use this trigonometric transform to disseminate the signal and break it back down into its constituent parts. So each peak in the spectrum is representing something that is rotating or radiating forces at that frequency. And the objective of this session is to show you how to recognize patterns. What you're doing in diagnostics when you're using an FFT analyzer is you're looking at the shape of that spectrum and you're looking for those troublesome frequencies. And there's no real black art to this. A long way to successful diagnostics is knowing what's inside the machine. So in the case of this gearbox, for example, it's nice if you have a cutaway gearbox and you can count the teeth. Life isn't like that. What you would have to do is go and get an engineering drawing and find out how many teeth are on each stage of the gearbox, so you can go and look for those tooth mesh frequencies. And so it goes on. And the idea is, if there is damage occurring to the gear teeth, perhaps there's wear or there's backlash, you expect to see higher forces. If you get higher forces, you get higher vibration, therefore you will see an increase in that particular frequency. And you're looking in the spectrum to see which frequencies have increased over time, for example. I say over time. I was a consultant for quite a few years. It's very common that you don't have the luxury of seeing a trend, of seeing the rate of deterioration of a peak. You just marched up to a machine, told that there's something wrong, and you have to make your diagnosis purely from the shape of the spectrum and harvesting a few bits of evidence. More of that later. So it's just reiterating that each and every rotating part is going to generate frequencies at the speed of rotation of those parts, and this is where we hear the word multiples coming in or orders coming in. The thing to note is if we have a variable speed machine, these peaks are going to move. So for example, if the running speed changes by 10 revolutions per minute and I have 22 teeth, 22 times 10, this blue peak is going to move by 220 revs and not 22. So bear in mind that the higher frequencies move more than the lower frequencies. And there's a webinar dedicated to variable speed machinery analysis, and we would use techniques such as waterfalls and colour spectrograms to make our diagnosis. An important note: when we're looking at the shape of the spectrum, we're looking at live spectra very shortly. Another important contributory factor to the shape of the spectrum that we're going to see on the screen of our instrument are the structural frequencies. What actually happens is when we start this machine up, it's radiating energy at all frequencies in the frequency spectrum, and there are going to be some parts of the structure that, like those frequencies, are going to have a natural frequency that coincides with the energy, and those frequencies get amplified. Classic example would be my brandy glass here. If I exert a burst of energy in the form of a pulse, the glass rings. It picks up some of that energy and it oscillates at its natural frequency. And all structures have natural frequencies. This glass of water, for example, table, anything. It really doesn't matter. So in this case, this machine, classic example would be the guard that goes over the fan, the notorious for coming up with natural frequencies. Very thin steel. They're only there to keep your fingers out of the fan so your fingers don't get chopped off. These things will ring like a bell. I was in a factory some years ago that made gearboxes, and out of curiosity, they had a cutaway gearbox in their reception area, and out of curiosity I went up to the gears and hit one of the gears with my pen, and this gear, to my astonishment, rang like a bell. So don't forget that when you've got a gearbox and you can't see those rotational parts inside the gearbox, those gears will be very lightly damped. And so it goes on. Another classic is the casing of the machine. Anywhere that there is a tendency for the structure to take up those frequencies and amplify them. Now, a nice thing about this is that these frequencies will be fixed, and that's useful to us when we're making our diagnostics. They're fixed on the day that machine is made. The natural frequency of something, natural frequency of a structure we've seen in previous sessions is proportional to the mass and the stiffness. So they don't normally change unless you change the mass or the stiffness. So here I've got a glass of water with a natural frequency. I've just changed its mass by drinking some of the water. So I've changed its mass, I've changed the frequency. That's the only time, 99.9% of the time, that those frequencies change. And we can use that to our advantage when we are doing our diagnostics. What's next? Right, so we're going to be looking at a signature very shortly. And we have to remember that signature there are two contributory factors to that signature. There are the forces, as we've said. So we've got the running speed of the motor. We expect that to be the biggest peak in our spectrum because that's the highest forces. If we're dealing with flexible couplings, the succession on flexible couplings, we might have 4 bolts in our flexible coupling. Therefore, we expect to see a high 4 times. That will pop up in the spectrum. And so it goes on. We might have blade pass frequencies and the like. We then have this thing called mobility, which usually comes from the parts I've explained, fan guards. If you're on a ship or an oil platform or up in a mezzanine floor, your machine might be mounted on thin plate steel. Or the classic example that we're going to illustrate is pipework vibration. People take a motor pump set without thinking. They attach pipework. They want to move fluid from A to B, gas from A to B. They don't think too much about the natural frequencies of these. And if they're really unlucky, what you'll get is the lightly damped natural frequencies will coincide with the big forces, and you get this thing called resonance. So one simple test that you can do is to stop the machine and do a bump test, which we will do. You do your bump test, and what you don't want is these sharp peaks to coincide with your running speed. If they do, you're in trouble. Just a tip, I said that this session is supposed to be on interpreting spectra that you see on the screen of your FFT analyzer. Just one tip for you. If you see a narrow peak in your bump test spectrum, that's telling you that that structure is lightly damped. That means it's ringing for a long time. My brandy glass rings for a long time. Therefore, the structure, the peak in the FRF is going to be very sharp. Same with this glass. In reality, what we're dealing with out in industry, what would you get on an electric motor? Well, we're thinking here there's a safety guard that's made out of, you probably can't hear it over the microphone, but this safety guard on this bench top grinder is very lightly damped. I can hear it ringing for a long time. If you see a broad hump in your spectrum when you're doing your bump test, that's telling you that it's something very heavily damped. My table, the case, the stator casing of this electric motor, that's very heavily damped. It doesn't ring for a very long time, doesn't oscillate for a very long time, and the effect that that has in the spectrum, when you look at it, the peak will be very broad. This is still a recap, by the way. So long for a recap. Why would you want to do diagnostics? Well, there are two main reasons. A red light comes on, and a warning light that tells you that that machine has deteriorated. You're doing your route-based data collection, you're trending the data, and something has started to deteriorate. The data's gone through the alarm limit, and you need to know why. Now, you could just simply go from the trend and say, oh, heck, the machine needs overhauling, strip out the machine and give it a full overhaul, and then put it back in. Or you could be a bit more clever, and before you shut the machine down, start to do some diagnostics, and in which case you might find that all that needs to be done is to balance the machine, or if it's misaligned, align the machine. So by doing some diagnostics, you can focus your time and effort in the workshop on the fault that's actually needs fixing. So that's one source of a traffic light. Another source is a simple test. There are people out there who don't trend data. I know this may be a fairly a dramatic thing to say, but there are lots and lots of people out there who don't do route-based data collection, who simply walk up to machines and check whether they're good or bad. We've done a session on the check to conformance module where we'll take a spectrum, apply an alarm mass, and find out whether the spectrum exceeds that mass. It's classically used by manufacturers who make machines and want to do a quality test of that machine. There are very simple products in the SKF portfolio. There's a thing called the Machine Condition Advisor, which is just basically it acts like a simple pen with an accelerometer, a battery, a display, and you put that on your machine, and it compares to the value that you get with ISO 10816 Part 3, which is general industrial machinery. We've had sessions previously on the machine condition indicator, which is a permanently mounted sensor, but it's just a simple measurement that you're going to compare with an appropriate limit. And in that case, when the red light comes on, you might need to know why has the red light come on, and that's why we do diagnostics. Right, that's the recap. Now we're going to start doing diagnostics, and when we do diagnostics, we're going to be gathering evidence. We have a hypothesis of what might be wrong, and we need to start gathering evidence as to the cause of the problem. And evidence comes in a variety of forms. It doesn't have to be vibration. It could be our noses. If we have a belt-driven machine and there's a problem with the belt, we might smell burning rubber, indicating that the belt's slipping. That's evidence that we have a problem. We might see oil on the floor. We have to open our eyes and ears and look at all kinds of evidence. Heat. We might use a thermal camera to look at what's getting hot. But the classic is to look at the spectrum and the motion of the machine. And this is rather excellent pocket handbook. It's created by Technical Associates of Charlotte, and thank you very much to them for allowing us to reproduce this booklet. This booklet is great because it can sit in the pocket of your boiler suit, and it is an almanac. It's an almanac of a whole range of machine faults. You get a paragraph explaining how that particular machine fault will manifest itself. You get a picture of the spectrum, and I said that diagnostics is all about the shape of the spectrum and the peaks that are there and the number of peaks and the frequencies. So it gives you the shape of the spectrum, and it gives you this thing called phase relationship. It's telling you the motion of how that machine is moving. And you can see here it conveys that information by giving a little circle with a tick mark. So unfortunately, I can't throw a switch and convert you people to diagnosticians in the space of a 1-hour webinar. I can't probably do it in the space of a 3-day training course. The best diagnosticians are people who've been out there for 2 or 3 years, walking around machinery, scratching their heads, wondering what's going on, looking at the spectrum, referring to the almanac, and then making their diagnosis. You can do it out in the field online, which I'm going to do, or you can do it back in the laboratory, and you can get a wall chart. So we can take this fault almanac and blow it up large size, about 6 feet by 4 feet, or where are we? 1.8 meters by some centimeters. And you can get this wall chart, which gives you the same thing. That's behind your desk, and you're looking at the spectrum, looking at the wall chart. Do that for a couple of years, and then you'll be a proficient diagnostician. But this, I'm being slightly frivolous there, but it is very powerful. As I said, one important thing in gathering our evidence is measuring phase. I'll use the example now, so rather than here's a classic example. In this photograph, you can see a motor and a pump, and we're going to be looking at misalignment. But as I said, one of the biggest sources of evidence of misalignment is relative motion going on between the machines. You've got 3 types of misalignment. You've got parallel offset misalignment, where there's a horizontal difference in the heights of the 2 shafts. There is angular misalignment, where one machine is off at an angle, and then there's a combination of the 2, where you've got parallel offset and angular. If that finger is an accelerometer on the motor, and that finger is an accelerometer on the pump, if everything is perfectly aligned, you expect the machine to operate nicely with very little axial vibration. The motor and pump go up together, they go down together, so everything is in phase. If there's parallel offset misalignment, what you'll get is a precessing motion going on. So as that accelerometer goes up, that accelerometer goes down, and you will get a 180-degree phase difference across the coupling. And that's what we would be looking for in that situation. Now, with an FFT analyzer, doesn't matter whose, there are 2 basic ways to measure phase. One way is to use a phase reference, and that involves stopping the machine, applying some reflective tape, as I have in this. I've got some reflective tape on my machine, so I've stopped the machine. There's some reflective tape, and you get yourself a optical tacho in various forms. This is a laser one. You mount a tripod, and you fire a beam of light at the shaft. And traditionally, that's what people have used, which is fair enough. Certainly, if you're going to diagnose unbalance, you have to do this method. But it is fraught with problems. You have to stop the machine. And when you're in a real environment, you can't always stop the machine. Paper machines, any machine, you can't stop them to apply some tape. So that's your first problem. The second problem is that you stop the machine, apply your tape, run the machine up, the tape flies off, goes over your shoulder, and you've got to stop it and start all over again. It's an arbitrary measurement, because the reading that we're going to get will be dependent on where we put the tape. So what we're going to get is a blip, a pulse, a trigger signal coming off the piece of reflective tape as it cuts the light beam. We're going to get a pulse, and we measure the phase from that pulse to top dead center of our vibration. That phase reading will be arbitrary, dependent on where we put the reflective tape. So going back to my diagnosis of misalignment, what you're going to do is use one accelerometer and a piece of reflective tape, and you make a measurement. You might come out at 63 degrees. You then take the accelerometer off the pump and put it onto the motor, and you take another measurement. You might get 63 degrees. 63 minus 63 is 0. That means there's 0 phase difference. My tiny little brain can't cope with 63 minus 180. But if you had that precessing motion, you'd have to be looking for a number which is 63 minus 180. And you can see the problem. Which is why I love the other way of measuring phase, which is the quick and easy way. You can use 2 accelerometers, which you apply to either side of wherever you're going to measure. You've got a picture here with 2 accelerometers mounted on the motor. 2 accelerometers mounted on the bed plate. I think there's another photograph somewhere. I don't know, I've got a bigger picture somewhere. Did have a bigger picture. Excuse me a sec. Sorry for... Oh, there we go. There's a bigger picture. Sorry. bigger picture. And while I'm here, I'll just do that. Do some editing of my lecture on the fly. Right, so there's a big picture of a motor pump set. So what you're going to do is mount an accelerometer on the motor, mount an accelerometer on the pump, making sure that they're both in the same orientation, and you're going to do something called a cross phase. Now, traditionally, when you looked at cross phase on an FFT analyzer, you would get the spectrum as we know and love it, and you would get this cross phase spectrum. But what we've done on the SKF microlog analyzer is give you this circle with a tick mark. So this display is actually giving you everything that you would ever want for making a vibration, or making a diagnosis using vibration, because you take this spectrum and that circle with a tick mark and you compare that with your wall chart or your almanac. I think without, I've been talking for a long time, so let's do a little demonstration of this thing called cross phase. I've got a little demonstration for you. I've got an electric motor here. I've mounted sensors in the vertical and horizontal. I have my analyzer. Just to quickly show you how this is done. So I'll do it right from scratch. You can see all the button pushing. You would probably recall the settings. So I'm going to do a magnitude and phase measurement. So I'm going to go new. I'm going to use 2 accelerometers. Whoops, would help if you could see me, wouldn't it? So there we go. Hello. So I'm going to use 2 accelerometers. The accelerometer type is a 2111. That's on both channels. And what I want to do, where it says spectrum and phase, that's where we would be using a piece of reflective tape and a laser tack. So the laser tack would go into the socket marked would go to the socket marked trigger, and the accelerometer would go into channel 1. So if it says spectrum and phase, you're expected to put in a tachometer, a laser tack. If we use cross phase, what we're going to do there is, without stopping the machine, applying our 2 sensors. That's the big advantage of this method. Using 2 sensors, we can walk up to the machine while it's running and apply our 2 sensors. And the other big advantage is 0 is 0 and 180 is 180. So if both accelerometers go up together and down together, you'll get 0. You're not messing around with 63 minus 63 is 0. If it's 0, you'll get 0. It's 180, you'll get 180, which is the other huge advantage of this. So that my tiny little aging brain can cope. So I'm going to ask for spectrum and cross phase. We'll take a velocity spectrum on both channels. We'll have a 10 Hz filter, so it's in accordance with ISO 10816. Oops, you still can't see, sorry. And so we've got spectrum and cross phase. We've got velocity on both channels, 10 Hz filter on both channels. And away we go. We should be able to start the machine. So the machine's running up. And I start my measurement. Gives me a chance for a slurp of water. So while we're here, we can kill 2 birds with 1 stone. Here's my spectrum, and we're getting a classic example of unbalance, by the way. In unbalance, what are the evidence that you're looking for? You're looking for a high reading. So the value of channel 1, the vertical, is 5.8 millimeters per second. For a machine this size, I would be expecting much less than that, less than 2.3. So we've got excessive vibration, first piece of evidence. It's the same in the horizontal plane. If I put my cursor on the running speed, and here's a tip, by the way, you'll notice that the circle with the tick mark is saying 180 degrees. Now, a trap that you can fall into is that's the phase at the cursor position. So what you need to do is put the cursor onto the running speed, and the quickest way you can do that is press the 7 key. So now the cursor has hopped onto the running speed, and I can see in this case we've got a reading of where are we? 5.48 millimeters per second on the vertical and 3.3 millimeters per second on the horizontal. So 5.4 of that 5.8 is coming out at the running speed. So the bulk of the vibration is at the running speed. More evidence that you've got on balance. There's a very little 2 times. More evidence that you've got on balance. That reading is very stable. Again, more evidence that you've got on balance. And in this case, the phase reading is very stable. You would be using a tacho type input for this, but that phase reading is nice and steady. So what you're looking at there is absolute classic shape of unbalance on a rotating machine. And you've got your phaser plots. If I move the sensor by 90 degrees, there we go. They're now 180 degrees apart, 178. So the 2 sensors are now opposing each other, and are getting a 180 degree phase difference. So while we were there, we just had a quick look at unbalance. And what else can we do? We ought to, while we're here, just quickly show you misalignment. So the shape of the spectrum in misalignment, if you look at the webinar on that session, we expect to see a high 2 times. I haven't got time in the space of this webinar to explain how it works, but if you were to put a strain gauge onto the shaft and you've got parallel offset misalignment, and look at the output of that strain gauge versus shaft angle, you will find that you'll get a double sine wave for 1 rotation. So you get 2 stresses for every 1 rotation of the shaft, and that causes a high 2 times. So what's the evidence that you're looking for in diagnosing misalignment? First bit of evidence is that you've got flexible coupling. Next bit of evidence, sometimes you can smell burning as that flexible coupling, the rubber in the flexible coupling is getting hot. The next bit of evidence is to put an accelerometer onto the machine and to look at the spectrum. If you see a high 2 times, sometimes a high 3 times, start to suspect misalignment. The trick I was told, or the rule of thumb I was told, is to look for the signal being half as high as the 1 times. In this particular case, the value is excessive. We've got 22 millimeters per second. That's way, way over our expected 2.8 for a machine of this size. So we've got excessive vibration. And we can start to measure phase. The way that phase works, just finishing off phase, if everything's in alignment, you would get 0 phase difference out of your 2 sensors. Sorry, lost the other one. You would get 0 phase difference. If there's parallel offset misalignment, you would see that circle with the tick mark move around to -180. And if there's angular misalignment, which is missing, again, it was missing this morning, it's missing this afternoon, that's because it's hidden. I do apologize. We'll unhide it. Apologies, folks. If you have angular misalignment, what happens in angular misalignment is you'll get a high 2 times, but you also get 2 more things. You get high vibration along the axis of the machine because the coupling is trying to force itself apart. So to diagnose angular misalignment, you need to take an axial measurement. And you will find that it's significantly higher than it normally is. You're looking at axial vibration to be way, way, way below half normal radial vibration. Normally in the machine, you'd expect vibration in the vertical and the horizontal and very little in the axial until you get angular misalignment, and then you start to get high vibration along the axis, more evidence that you're trying to gather. And when you do your phase reading, you're going to get 180 degrees because what's happening is that coupling is trying to force itself apart. So as the motor goes in this direction, the pump is going to go in that direction. So you'll get 180 degrees phase difference between the motor and the pump. Don't do what I did. What you're going to do to do this measurement is to put your transducer, your accelerometer, onto one face of the electric motor, and quite often it's convenient to put the sensor onto the face of the pump. Now what I've done there is a glaring mistake. You've inverted the accelerometer, and when you invert the accelerometer, you actually get a 180 degrees phase difference induced, because one is upside down in relation to the other. So it's important, if you're going to use phase, using two accelerometers, keep the orientation the same. So one transducer would go onto this face of the motor, and the other transducer will go onto this face of the pump, not on that face, so that they're both facing in the same direction. That way, if there's 180 degrees phase difference, you will measure 180 degrees phase difference. So far, so good. What I'm going to do on this instrument is to cheat. I can give you a spectrum that looks like misalignment. So I'm going to cheat slightly. I'm going to put my transducer on the tool post and see if I can get you a high 2 times. So running up the machine. Give me time for a slurp of water. So you should see, with a bit of luck, on the upper trace now, there we go. On the upper trace, you can see that we've got a high 2 times. How do I know that's a high 2 times? If I put my cursor on, my harmonic cursor, I put my cursor on the running speed, 2, 3, 4, and so on. That peak is the 2 times. And this leads into a nice little demonstration of an electrical problem. Because what I've got here is a high 2 times. In the UK, where the supply frequency is 50 hertz, that would be 100 hertz. What I'm going to do in a second is a switch-off test. Another classic test that you do when you're harvesting evidence by your diagnosis. One classic test you can do is a switch-off test. Now, if that was misalignment, and this machine is running at 3,000 revolutions per minute, it's misaligned at 3,000, it's misaligned at 2,900, it's misaligned at 2,800. So when I switch off, I would expect those 2 peaks to move left across the screen as the machine slows down. I'll move the cursor out of the way so you can see. What I'm going to do, what I want you to do is to look, I'll put the gain up a little bit. What I want you to do is look at what happens to the 2 times when I switch the machine off. It disappears instantaneously, and I'm just left with the unbalance. There's the unbalance getting slower and slower and slower, and my machine's running down. That 2 times has dropped radically. If I switch it back on, you'll see it reappear. Comes back instantaneously and disappears instantaneously. That is classic electrical type issues. Very frequent on electric motors that are getting tired, where the lacquer holding the windings is not holding the windings correctly, or if you've got wooden wedges holding the windings. If that hand is the slot where the winding sits and that finger is the winding, what you want is the lacquer to hold the windings stationary. But with age, the winding starts to move, and for one cycle of supply, you'll find it moves over to one side, comes back, moves over to the other side and comes back. So for one cycle of supply, you'll get 2 movements, slap, 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 slap. And that's why you get a high 2 times in the vibration spectrum. And you can prove it's electrical by doing the switch-off test. Again, this is using an FFT analyzer to detect or harvest evidence for your diagnosis. And last week we did motor current analysis, and I'm sure that would have manifested itself in the motor current spectrum as well. 2 last things to show you before the hour is up. One is a structural test, and I'll do that one live for you. So we'll do a structural type measurement. What I want to do is concentrate on one spectrum. So what we'll do is we'll come out of here We'll put our transducer onto the structure. Sorry, we'll recall the settings. Excuse me, I guess you can see that. So we're going to go for just concentrate on one channel. Wonderful, we'll leave it at that. No, we won't. We'll have a logarithmic y-axis so you can see what's going on. So I'm just going to change the y-axis of my display to a logarithmic display rather than a linear display, so I can show you this functionality. And we're going to take a basic spectrum of the machine running. Oh, we might want some averaging, by the way, so let's do some averaging. Averaging, let's take 10 averages, and we'll do an exponential averager. So we start our measurement. I've just got the transducer measured in the vertical plane, simple electric motor. Here comes my spectrum. We don't panic because this is a logarithmic y-axis. We'll do some averaging. I'm going to put my cursor on the running speed, 50 Hertz. I'm going to switch on my harmonic cursor, which tells me where to expect multiples. So we've got 2 times, 3, 4, 5, and so on. If you look in the spectrum, there are various places where the peaks don't line up with the harmonic cursor. There's an area down here, there's a peak in here. Let's go for this one this afternoon. So I'm going to switch off the harmonic cursor and go and put my analyzer cursor on that. So there's a peak in here which doesn't line up with the harmonic cursor. It's coming out at 315 Hertz, which is not an integer multiple of 50, which is evidence that that is structural. If it was a gearbox and there was a funny gearbox ratio, it might be some kind of funny gearbox ratio. But what the classic test you can do is to stop the machine. Hope there's no safety officers watching because I'm slowing this machine down to speed things up using my fingers. My fingers get very hot. Ouch. Very painful. So you stop your machine. In structural testing, we talked about doing a bump test. If you see the cursors there at that point, so all you do is you take some suitable implement, workshop hammer, whatever, and you do your bump test. And what you're going to be looking for is the part of the structure which coincides with that particular frequency. We'll do the left-hand tool post. Oh, left-hand tool post is very close. Let's try the left-hand guard. Hours of endless fun wandering around with a hammer trying to find out which component it is that's causing the grief. Usually the guard that goes over the fan, or belt guards that go over fan drive belts. They're the usual culprits that you would hit first. And the trouble starts when these frequencies coincide in Europe with 50 or integer multiples of 50, or in the USA 60 and integer multiples of 60. So a bump test is a classic test that you do in true cookery program style. Here's one I prepared earlier. So the blue spectrum is the spectrum of the machine that you saw when it was running, and the red spectrum is the bump test, and you can see, yes indeed, that peak in the spectrum when it was running is due to this natural frequency. There's a dip here where it's quite immobile, there's a dip here in the running spectrum, and so on and so forth. The last little demonstration to finish off with inside the hour is mechanical looseness. I think, yes. Mechanical looseness. There is a session dedicated to this, but I'll do a quick one for you. Mechanical looseness is another classic. It's where parts become loose. The name is self-explanatory. It's where maybe the bolts holding the machine down to the bed plate become loose. There's a weld in here, which has welded the bed plate to the foundation. Those welds can crack. Usually it's a cause of excessive unbalance. Excessive unbalance creates higher forces. Those higher forces create higher stresses. Those higher stresses cause things to break. And a classic would be to see a broken weld. You don't need an FFT analyzer, just your Mark 1 finger. If you put your finger onto the weld or the broken weld and you feel that finger being nicked, that's telling you there's mechanical looseness. But anywhere where there are bolts that can become loose. Classic is masonry bolts into concrete foundations. Those masonry bolts become loose over time. If you do your phase measurement, by the way, you put your transducer on the machine side, put a transducer on the foundation side. If that bolt is really tight, you should see both accelerometers going up and down together. So you've got your bolts in between those two positions. They're going up and down together because there's no looseness. If the bolt becomes loose, you're going to get relative motion. So anything over 30 degrees, either side of a masonry bolt or a bolt, is telling you you've got looseness. The spectrum, what are we looking for in the spectrum? There are two things that are going to happen to the spectrum. One of the first things is you're going to see lots of harmonics, 2 times or 3 times, and so on. And the reason for that is that you're getting metal-to-metal contact. Normally, for good motion, you're getting sinusoidal motion, but when you're getting metal-to-metal contact, that motion is truncated. And those electronic engineers among you will know that if you take a sine wave and truncate it, you start to generate lots of odd harmonics in the frequency spectrum. So that's what we're going to see from our mechanical vibration. The worse that mechanical looseness, the worse that truncation, the more harmonics we're going to see. And because we're getting an impacting type of signal, an impact creates a burst of energy through the whole spectrum. So we might see the whole spectrum come up. So let's conclude with a quick demonstration of mechanical looseness. I'll set up to do that. So we'll exit out of here. We will go to recall our settings. I want to do a 2-channel measurement again. They're both 2111s. As I said, you would recall your settings. I'm just doing it manually so you can see the settings being changed. Cross phase, pardon me, 2 velocity spectra. Well, we'll see how we go with that. Yeah, we'll run with velocity spectra. I think that's us. Yes, yes, I think that's good. So we want to, and I've put my transducer onto the tool post because what I'm going to do is loosen the tool post to see what effect that has on the vibration spectrum. So we start our machine. Press start on our analyzer. Take a slurp of water. Oops, it's still in logarithmic. Sorry. Do apologise. Need to get rid of that logarithmic y-axis. So there we go. There's our vibration spectrum. There's the 2 times that we see on the tool post. I'm going to put the cursor onto the running speed. The phase is running nice and steady at 12 degrees, and the amplitude is nice and steady at 13 millimeters per second. And now what I'm going to do is just loosen the tool post. And you can see that the phase is starting to move now. It's become unstable. It's not nice and steady anymore. It's moving. It's gone from 13 to 23, 28 degrees. So we've seen a phase change, and it's not working very well this afternoon. Let's try and get a rattle for you. Things won't rattle when you want them to rattle. See if we can get a rattle. Sorry folks, we'll get there. There we go. So hopefully you can see, if you're looking at the baseline of this spectrum, you can see there's all this energy down here. That's the impacting going on, creating those bursts of energy that bring the spectrum up. And you can see from time to time, there they are. There's a bagload of harmonics. They come and go as the rattling comes and goes. And if I tighten this thing up, so I'm going to tighten up the tool post, you see all that energy disappear. It's dropped away now. And the phase reading has now gone back to being stable. Oops, sorry, it's still got a little bit of looseness. There we go, got rid of it. So there we go. The baseline has dropped back to where it was, and the phase reading has gone back to being stable. One last try. Loosen the tool post. The phase reading should become unstable. Yes, it has. It's gone from 3 to 19, and we're starting to get this background energy across the base of the spectrum. So, hopefully, in the almanac, there will be lots and lots of different types of machine fault. I've tried to give you a short view of the common ones. Unbalanced, we're looking for stable readings, high readings. Mechanical looseness, we're looking for lots of harmonics and an increase in the broadband signal. Misalignment, we expect to see a high 2 times, a high 3 times, and we especially want to look at the phase, to look at the relative motion. Electrical problems, if you switch off the power, they disappear instantaneously the instant you switch off, and so it goes. It's just really a case of getting out there with your FFT analyzer, looking at the machine, and trying to harvest as much evidence as you can, concentrating on the shape of the spectrum and the phase, but that's not a panacea. Use your nose, smell for rubber, burning rubber, use your eyes, look for things getting hot, use your fingers, and so on. So, for the benefit of those people who are watching the video, I hope that's been useful for you, and thanks for sparing your time, and cheerio.